Yeah, it's nice to be invited to come and give a talk and kind of an overview of work. And there's a few people in the audience. Andy, who's the organiser, and Armin over here, whose work this really is. I'm just the front person on this. My interest and, I guess, activity has been much closer to the 3D than the deep learning. But then, of course, for all of us, the deep learning and what's happened over the last 6 years or so with deep learning has radically changed the field. So I'm going to give a little snapshot of that in terms of our work, and particularly work around 3D and 4D, which I'll explain in a minute, and how that's kind of impacting our work, although I wouldn't claim to be an expert in deep learning, but it's, you know, our problems are now defined in terms of the things we can do with deep learning, and that's both in terms of kind of algorithm development, but even more importantly, probably in terms of data sets and access to data sets, and that's where, you know, most of the time actually the limitations are for games and things like that, but it's also important in terms of a non-contact measurement device from video, which might be used in things like medical applications. So we're very interested in non-contact monitoring in that context, where the state of the art is still to stick ping pong balls all over someone to measure their movement, and that really is the state of the art, and it's very tedious to do. But this is also important if you think about all the bits and pieces that need to go into the ability of a robot or an autonomous system to be able to interact with people in their home environment. You know, one of the things they have to cope with is the crazy dynamics of people and them doing things and the unstructured type of environment. And in my opinion, we're still quite a long way from being able to deal with those things through sensors like vision. You can get a bit further with depth imagery, but it's still a lot of complex data and a lot of relatively uncontrolled complex data. So that gets us to 3D anyway. And what I really want to talk about is 4D, which is essentially taking that 3D and knowing where everything moves over time. So it's adding a time dimension in. So the guy on the right-hand side has now a lovely flower pattern attached, and that's really representing the fact that we have correspondence over time. So we should know where the tip of his nose is at every instance, etc. And that's a key step in terms of being able to then analyse the data, extract any information from the data, or indeed represent the data in a way that you could use it in, let's say, an animation pipeline for a game. Yeah, so that link is really key. We were here, well, at least 10 years ago, maybe 15 years ago, in the lab. It's taken us a lot longer to get to this side. It's probably another 10 years of work. And that's an area we're still working on. So this is kind of a snapshot of what I'm talking about in terms of 4D. Of course, the interest is not really to do it in this kind of lovely controlled environment. It's to be able to do these things in a room like this or in a street, like the street outside, and really pick up this kind of information. So that's the kind of 4D vision in the wild as opposed to the lovely controlled conditions. So one of the things we've been able to do, going back a dozen years now, is to do this sort of thing and capture large data sets. So this is one of the things that's potentially useful for training purposes as well. And this work goes back to 2007. I think actually the work was done even before that. And John Stark's work at that stage, the key people in the development of this. One of the things we've done from that, going back a few years, is then to create animated representation. So the motivation here is very much on content production and using this kind of 4D pipeline from video through to things that you'd render as a controlled animated model, but try to maintain that realism that you have in the captured video. And this, the steps in this are actually the key things in order to use this kind of video in any kind of content production, because you need the 4D representation, for instance, to be able to edit data. So this very much links up with applications in film production and that kind of thing. But again, these are all done in nice controlled studio environments. And then one of the, I guess, current applications for that is to take that kind of content and put it into an augmented reality type setting. So this is a simple kind of street scene setting with some characters imposed. And, well, they were captured from video, so they look kind of like video. They don't really fit into the scene. The shadows are kind of a starting point, but the shadows aren't properly blended in. There's much more you could do in that context, but it's a kind of example of what you might do. What we don't have at the moment is the ability to do these things. The animation itself is in real time, but what we'd really like is actually to be able to impose this using a HoloLens and have another person there who's able to interact in real time. And it's not just us who wants to do that. Certainly the folks at Microsoft and Facebook are looking at exactly those directions for this kind of technology. And the big team that's working on HoloLens, exactly those kind of things, as well as scene mapping, where the field is much more mature. This kind of dynamic content mapping also comes into that. Okay, so hopefully that's kind of just some snapshot examples of results we have. My interest in kind of 4D and talking about 4D goes back to, well, actually this is the inherent structure of the world around us, and there's lots of applications that stem from this. Our work happens to have been motivated primarily by entertainment industry over the last 10-15 years, but there's lots of other applications in terms of having autonomous systems, having measurement systems for healthcare. Simple things like monitoring sleep is one of the probably widest spread potential applications of this kind of technology, which you think is not it's not the thing that's driven the research so far, but it's an area where actually having this kind of information could be very useful. I already mentioned the human-robot interaction. Okay, so I'm going to talk a little bit about how we obtain, I guess I'm going to talk a lot about how we obtain these 4D representations. Mainly around multi-view data, because that's where the bulk of our work is, and that's where the field has advanced most. Ideally, you'd do all this from a single video feed, because that's the most flexible input, and there's some great work on things like non-rigid structure from motion, but it tends to be quite limited in terms of its reach and the quality of the output models at the moment. Of course, that's where we want to get to, and there's probably some examples today from others in the room where that's progressed much further. And there's certainly a nice example of work from our lab in that area. Depth imagery helps as a starting point, simplifies things. I think when cheap cameras like the Kinect first came on the scene, the vision field did the typical thing of everyone jump on that bandwagon, and then 5 years later realised that actually this doesn't really solve my problem, it just gets me the first step. Yeah, so it's nice, and those things are still used, but they don't really get you to the end result of a structured representation of what's happening in your scene over time, which is what you need. You know, that's what you need as the output. So, equally you could use stereo or multi-camera systems. We've used multi-camera systems a lot, which go anything more than 2 cameras, I guess. The initial reconstruction is only the first step in this pipeline, and it's probably the one that's had the most focus from the field. And it's the one, I guess today, if you pick this up, you'd use some form of deep learning-based stereo to get your results if you're using video images. But then you've still got to go through these parts, which are probably less explored. There are some results in those areas to obtain this kind of structured 4D representation, which is really the thing that interests me. Okay, so I guess just to convince everyone that this is potentially challenging, There's lots of things that occur in the real world that we really steer clear of in terms of a lot of vision work. So these are some of them that we've tripped over, I suppose, along the way. I'll show an example in a minute of sports work where you're dealing with large volumes to capture, so 100 meters by 50 meters with some tiny little people running around on it. That's one of the areas where it would be really nice to be able to do this stuff well, but it's still very much in development. Fast motion, when you're dealing with conventional frame rates, of course you get high-speed cameras, but that adds to the expense, it adds to the specialization. And typically, for these things, you need moving cameras, backgrounds are changing, illumination's changing. You have non-Lambertian surfaces. A lot of our algorithms still make some fairly simple assumptions in terms of either stereo matching, assuming Lambertian surfaces, or optical flow type algorithms for doing things over time, where actually if you're really dealing with the scene, usually the first thing that happens when you do a piece of production work is they come in with costumes that don't fit your model. There's a great example on one of the other slides of doing chainmail. Our system wasn't really designed for doing chainmail, which has lots of complexity to it, but it certainly breaks all the assumptions in the algorithms. Fortunately, in that case, we were able to get some reasonable results at the level that we did things. But it was an interesting experience. I put this example up at the bottom here because this was an example where we were due to do a piece of production work in a nice green screen studio, and literally the day before we were doing the shoot, it changed to a sand quarry, which wasn't great for our cameras. They probably never really forgave us for that. But it also created a lot more complexity. On these images, it looks like the toga is quite distinct. Actually, when you come to trying to segment that from the background, the colour component is very similar to the background. There's kind of the things that could be simple if you can control the situation, but there's many situations where you can't control. Film production work is probably the one that we've tripped over most, where actually the importance of visual effects to the final film, they're very important. To the production crew, they're not important at all. You just capture some footage and do your magic later on, and that's, you'll do that with whatever you do. Placing cameras and things like that, controlling backgrounds, is not in the consideration of the director for the movie, usually. Okay, so what I want to talk about is outdoor 3D capture and some of the lessons we've learned there, and then move on to some of the more recent work on 4D, and doing that in uncontrolled situations, just to illustrate some of this. There's at least one talk later on today that will link in some more of the detail behind this in terms of what we're doing, and I will pick up on where some of the deep learning techniques come into this work. So the basic problem, going back a few years, that we looked at was, okay, if you've got a set of multi-camera views in a relatively unstructured scene, this happens to be an indoor scene, but the backgrounds aren't controlled, so you've got multiple camera views, how do you perform reconstruction on that type of thing? And ideally, you want to do that without knowing anything about the background, anything about the camera calibration, because the camera calibration is a bit of a pain to do, and cameras get kicked and things like that. So one of the first things we did in terms of solving this, or looking at this problem, was to look at two problems together. The first one is segmentation. And the problem with segmentation is even with the most sophisticated techniques, using all the deep learning you like, it's still an ambiguous problem. You get a black piece of clothing against a black background. Where's the boundary between the two? You just don't have the information there, unless you have some form of priors, for instance, on the shape and things like that. But once you have multiple views, you also have a problem of reconstruction. And actually, I suppose our insight, going back some way, was that actually those two problems are joint problems. If you solve the reconstruction problem, that helps the segmentation. And if you solve the segmentation problem, that helps the reconstruction. In this case, because we've got multiple camera views. So we were keen not to put constraints on what we're actually seeing in the scene, because as soon as you do that in terms of a model, you find, well, actually this person's now wearing some clothing that doesn't fit that model, or you're dealing with an animal or something that doesn't fit the model. So one of the insights was, well, actually solving these problems together is important, and it gets you further. Now, the reason for dwelling on that is because that insight will come back later on in terms of how we're using deep learning and what we can do with deep learning, both now and in the future, to kind of pull things together, I suppose. But this is a non-deep learning framework going back a few years. Just show kind of some examples of how we dealt with that. At this time, we were learning information about the background, which then allows us to do some initial segmentation, which isn't perfect. And we're also using stereo cues. And at the time, we had a classical now graph cut optimization that pulled these cues together to form a reconstruction. So this one is the initial visual hull segmentation intersecting the segmentations from the set of views. It's kind of classical vision now. So we end up with energy optimization with some 2D cues and some 3D cues. I'll just put those up. So we've got things like foreground, background color and contrast, which is pulling out the edges of the scene. And then this is a classical stereo normalized cross correlation term in there, and then some surface smoothness term. So a very classical way of framing an algorithm. Yes, I guess now you put all those things into your loss function and optimize over your data set. So what that's doing is then estimating essentially a per view depth map for these scenes. I'll show you some sequences in a minute. And that goes from the initial segmentation of this very blocky visual hull through to something that, well, is certainly smoother and has a bit more detail to it as well. Not completely perfect, but much better than what you get. Interestingly, if you just do stereo on this kind of data, and this is true of deep learning stereo as well, you get something that's pretty noisy. So the solution is not just to optimize your stereo. So the key thing to understand here, I guess, is that what this is doing is optimizing over those two things. It's optimizing the segmentation and the reconstruction at the same time. And this is the kind of data, 3D data, you get out of that. You can see some flicker here. It's certainly far from perfect, but it has a lot of richness in terms of detail, in terms of clothing and things like that. But purely in 3D at the moment, purely 3D geometry in each frame. Okay, so one of the motivation behind that was a sports application. And this is work we did going back 10 or more years with the BBC, where you'd like to be able to do this kind of thing in a sports stadium, very large area, and essentially go through the same pipeline. And the motivation for that is to do both annotation on the pitch, things like that, and match commentary, where in this case they wanted to have virtual camera views around the stadium. The challenges of this are that, well, either you frame your cameras very widely so that they cover the pitch, or cover half the pitch, and that's one option, but then your people are tiny, or you use moving cameras, but you then have to calibrate somehow. And you think, well, you could put sensors on your cameras to calibrate them. Not really a viable option. That is done some of the time at the moment, but it's expensive to do. Adds a cost. So what we're doing here is solving for the calibration as well from the pitch lines and that kind of thing. So this is technology that you'll see from the BBC, and you'll see has been licensed to others as well for use in commentary today. And I'll just play through some of the results. So the first thing that should come up is the actual match cameras. And you can see they're pretty small. This is probably HD footage at the time we did this. So the first challenge is this segmentation, and this is the joint framework. And what we end up from our technique is this one down here. There's a couple of other examples of segmentation techniques there. But this is what you get from the kind of joint optimization. And hopefully people have arms and legs, which is kind of important for the reconstruction. And then the bottom row here is 3 different variants of the reconstruction. If you just do the kind of naive thing, you end up with this, where actually you get usually the core of the person, but because the calibration of the cameras is not brilliant, so if you get 1 pixel error in calibration, that can easily be someone's arm. So yeah, this is the kind of thing we got. Just putting some colour on, and then in a minute it will go through to the final result. So it's interesting to note these results were from 10 years ago. This problem still hasn't been solved. So you'll see examples of use of technology. If you watch football, you'll certainly see examples on TV. Usually the examples are for a single frame, where you freeze frame, and then and the reason for that is then you can have someone manually correct things. So the systems that are set up are very much along those lines. I talked over the free viewpoint there. Okay, just give some examples of what you can do with this kind of classical framework. Wrong button. Okay, so that was 3D and some examples of where we got to. So what I want to now talk about is more into 4D. So the same setting in some way, but trying to generalize this problem, so more general scenes. And in this case, moving cameras, potentially handheld cameras and things like that. So all we're given at the start is a set of camera views, and we don't know anything else about what's going on, other than they should be looking at the same area of the scene. So this is an example from ETH of 6 handheld cameras for this. And I should say this is Armin's work. If there's any difficult questions, then refer to Armin. So this is the work she's been doing over the last few years, which I'll give a snapshot of and bring this up to date. So the idea is to go from this still multi-camera footage, but without any prior information, and particularly priors on camera calibration and scene background. Well, the 2 things we want to avoid, because they're difficult to get, they change in reality, and they break the algorithms unless you control them. And then the output from this should be a 4D scene reconstruction of the scene objects and how they move over time. So this is kind of the overview of the system. So you've got your multi-view input here, and then there's 2 larger boxes here, and it's important to, I guess, the reason for splitting things up is that what the approach does is does a global scene reconstruction, and then particularly because we are interested in the dynamic elements, it then does an object level reconstruction of individual elements within the scene, and that's quite important computationally in the algorithms when you're doing this on larger scale dynamic scenes. So the first problem the method faces is, well, I've got to calibrate my cameras because it doesn't know anything about that, and in order to get geometry out of the system, it has to know the relative position of cameras. So what we did quite a lot of work on was actually getting some sparse features that we could match across relatively wide baseline unconstrained views. So that's this part here. and then those are clustered to identify objects. And that gives us a starting point for the detailed scene reconstruction. Now, that might seem like, oh, that's kind of straightforward. For us at the time, everything we'd developed up to that point was based on segmentation of the scene first. Yeah? There is no segmentation here. It starts from just matching points between images. And that's a fundamental difference of doing things this way. And it removes a fundamental limitation of all the work we did previous to that, which was that we had to somehow constrain the scene by constraining the background, which is lots of situations where that breaks. And then this side is then going from some initial coarse reconstruction to much more detailed reconstruction, and then tracking over time to get temporal coherence. So I'll show first of all a result of that, and hopefully you'll say, well, this looks very similar to the results I showed earlier. It should, hopefully, but there's a big difference here. We haven't told it anything about camera location, segmentation of the scene. We haven't set things up for it to be able to do that. And the results are pretty much the same in terms of geometry and that we get out. Okay, so that's kind of at a very high level the overview of that part. One of the things I want to talk about is the importance of utilising information, I guess, across the sequence. And one of the things that in this work we showed, I guess, was that actually to reconstruct any individual frame in isolation is quite difficult. But what you have, if you have a person moving through a scene, you have a lot of information over time about what that person looks like. And actually you can combine that information across different time frames, different frames, as long as you can somehow relate them. Yeah? So this was a piece of work which Armin did, which was to effectively, again, in a situation where you don't know what you're looking at in the scene, to match up frames so that you can use them as priors. So you can learn priors for your reconstruction, effectively to constrain. So something called 4D match trees. So the assumption here is that you've got some initial reconstruction and you've got video frames. And what's effectively we've done here, or Armin's done here, is to take some feature matches at different frames and relate them across where they're not consecutive frames. So it's a similar problem to the problem of if you've got widely spaced camera views, how do you match between those views? Yeah, so that would be a wide baseline stereo type setting. This is a wide time frame setting. Of course, that means that things will have changed because then the orientation of the person may be different, things like that. So it's a slightly less constrained problem. But the idea here is to use a set of feature matches effectively to relate frames and compute some form of similarity measure. And then from that similarity measure, to then restructure your video sequence, or your temporal sequence that you're trying to reconstruct, so that you relate frames that are close to each other. So, for instance, if you've got someone walking through the scene, then every cycle of the walk they're going to repeat. You can relate those frames, and the reconstruction for each of them should be similar. That's the intuition behind it. Okay, so the idea is once you've got this kind of sparse feature matching, you can then go from that as a starting point. That's the difficult bit, in some sense. You can go from that to a dense correspondence and fill in the gaps, and that applies to both reconstruction and temporal correspondence. So what you end up with at the end is hopefully everything aligned and this kind of 4D temporal consistency. So I'll show some examples of that kind of thing. What else to say about this? So in terms of what we're using to do this, so we're using a feature descriptor, a feature detector that Armin came up with that's good for wide baseline matching, so what's called SFD there, and then using SIFT descriptors because they're very good. The problem we found with just using off-the-shelf, I guess, feature detection is in these situations you don't get enough features. Commonly you end up with, if you just take most feature detectors, you end up with all your features in one part of the scene and nothing elsewhere. And that, for reconstruction, for camera calibration, that's really bad. So we kind of went back to the feature detection problem and came up with some new ways of doing that. And this is actually a feature detector that's based on segmentation of the scene, which is something that's typically very unstable, but actually using certain properties of the segmentation you can get features that across the whole scene they're more widely spaced and don't depend on global thresholds and things like that. And that's, I suppose, the nice property to flag up. So from that set of features we compute a similarity matrix between all the frames, and then we compute this tree that allows us to align the data based on similarity. Okay, so I'll just show some examples for that. Again, the similarity matrix, I showed this already. So the steps are to compute the similarity matrix and then to compute effectively shortest paths through that tree to then perform the alignment. Yeah. So what that gives you in a situation like this is here's your features that are kind of popping in and out, what you would expect to. Then you've got this alignment across frames, identifying similar frames. And that allows you then to get this dense point, and the colour coding here is just showing you've got correspondence over time, or this is the correspondence in 2D, and you can see that it's a dense correspondence. Of course, you have to think about what's the definition of correspondence here, underlying this. Are you really getting exactly the same surface point? Of course you're not. You're getting something that's still based on appearance that is in the same region and looks similar. And if you've got certainly non-Lambertian surfaces, or actually even with Lambertian surfaces, the shading will change, and that will affect your match. But the good thing here is it's a way that allows you to do this without too many priors on what you're seeing in the scene or the setup of your cameras, because everything's being computed on the fly here at each frame for the moving cameras, for instance. So you can see in this frame the camera moving around. It's just a handheld camera. And hopefully at the bottom here you can see that although there's a lot of noise in here in terms of reconstruction, from a very small number of views, the correspondence is holding up quite well. Okay, so that's introduced a couple of things, ways of doing reconstruction for less structured scenes and ways of doing temporal correspondence. Okay, so up to that point we've avoided a deep learning. Well, not avoided, we just haven't exploited what's there. So what I want to do now is just introduce some bits where deep learning starts to come into this, actually to feed information into this kind of reconstruction, which is one of the areas where it's useful. And that will hopefully lead on to where we're going in the future in terms of use of deep learning as well. One of the pieces from, 2 years back now, was to look again at the segmentation and to exploit the work that had gone on in terms of 2D segmentation and semantic labeling of scenes. So the ability of deep networks to place labels on scenes that say that's a floor, that's a person, etc., which is one of the things that are demonstrated to be very good at. So again, taking sequences like this. Okay, so again, the same kind of setting. So we've got a set of input videos, and what we're going to do then is use our deep learning and this kind of state-of-the-art 3 years ago to obtain some per-view segmentations. And typically, because the problem is ambiguous, you get some fragmentation. So this was the state of the art 3 years back. If you use last year's state of the art or this year's state of the art, you will do slightly better than that, but it will still make some mistakes. Yeah. So now the idea is to effectively use our framework to combine the semantic labels for the scene as well. So we're refining the semantic labeling at the same time as doing the reconstruction. So it comes back to the same kind of intuition. Again, we obtain an initial reconstruction, it's quite coarse, but that then allows us to propagate information or combine information across views. And the idea would be to get rid of some of this fragmentation, because it's not consistent. The mistakes aren't consistent across views. The other thing we can do, of course, is using this temporal correspondence, this stuff I just talked about with the match trees. We can use that to relate frames across the sequence as well. So that's what we're calling semantic tracklets here. It's based on the same kind of framework. That then goes into an optimization with all these terms. And I guess the difference here is that we've now got this semantic label term in our optimization. It's the same kind of framework with a graph cut solution. And what comes out of that is now a refined reconstruction and a refined segmentation across the scene, and the ability to relate different frames to improve the reconstruction. So it's combining all that information together. And just to focus on this slide, this is the kind of segmentation that comes out of this, so out from the reconstruction. So the comparison to make is between these frames here and this column here, which was the input segmentation. So you can see a lot of noise here, whereas across here, most of the noise is gone, and the boundaries for something like the person there are much more accurate in terms of the reconstruction. Again, without knowing what the backgrounds to the scene are and that kind of thing. So playing video. So going back to this scene, this is kind of the semantic segmentation. This is an earlier work, so this one's actually a refinement of that. And again, the kind of reconstruction you get out of this. Again, preserving the kind of dynamics we have. Just another example of outdoor scene again. And yeah, reconstructions, in this case 2 people, and the segmentations we get from that. There's all refinements of the same kind of results and generalization of the approaches that we're using to solve it. So trying to minimize the amount of prior information we have to put in the system, or prior constraints, I would say. Again, another example comparing some of the segmentation results and showing some of the errors that the earlier work would have made, but now combining in this semantic segmentation, which is a very powerful tool to use. Then you can, in these situations where actually you've got quite blurred imagery, as you can see on the top, you get out quite nice segmentations and corresponding reconstructions. Okay, so that's, I guess, where we got to in terms of published work on this particular strand. So I wanted to talk a little bit about more recent work that we've done on that and just show some results from this. But I think the thing to say is that the deep learning techniques have delivered lots of different cues that we can pick up on. And so the route we're going down now is to combine those cues within a single framework, because, for instance, if you estimate the pose of a person, that's going to help your reconstruction, and that's going to help your segmentation. So you can feed that information in. So we're using human pose priors, using things like open pose to track, which everyone else is using, of course. Very powerful 2D pose detection. Doesn't always work, but when it does, it delivers you some additional information that you can use. At the moment, this is at the level of taking a lot of these things and then feeding them into an optimization that combines them, so a more classical optimization. The ideal going forward is that actually you learn all these things simultaneously, if that's a tractable problem to solve. May or may not be, I guess the jury's out on that. You can feed in things like instance level segmentation, which is identifying, for instance here, that you've got two people in the scene and you're separating them out. That can actually go down to also body part segmentation. And then, where that helps is when you're doing your tracking of the surface, then to have, to separate the people out so that you don't confuse between them, which is one of the challenging problems as well. So that's a bit of a, I guess, in terms of semantic segmentation, this is a bit of a refinement of what you're doing in semantic segmentation to put instances in there as well. Okay, I'm just going to, hopefully this will play. Yes. Okay, so this is kind of an example of nice control conditions, kind of the instance level segmentation, and the one at the bottom is playing. And then it is playing. Okay, and the kind of reconstruction, and with what I've shown before, without the instance level segmentation, you wouldn't necessarily be able to separate the tracking of the two objects. They'd get confused. But this helps in terms of the instance level segmentation. Okay, another example, which we'll see some more results on later. But this kind of ability to track multiple objects. These two are set in scenes. You can also apply this to the kind of unconstrained outdoor data and things I showed earlier. Okay, so that's really where we've got to in terms of 4D reconstruction and trying to remove constraints and building in advances in deep learning into this. You could argue that, well, it's not an integrated system at the moment, and I think that's where we are in terms of the kind of state of the art. One of the challenges there, just going back to the beginning, is getting data for this kind of thing that you can train from. Where you've got data with all those different labels is a challenging problem. Given the data sets, you can probably then train. Okay, so I want to move on from that to some recent work that was published at ECCV last year. This is the work of Andy Gilbert, who's hosting the meeting today, I guess. So I'm going to give a snapshot of that and show the results. Andy's going to talk a bit more about the detail later on. And I want to explain what's here and also from my perspective, why this is a kind of important step for what we're doing. So everything I've talked about up to this point has been using quite large camera sets to do reconstruction. So typically 4 to 8 cameras we use. This is a piece of work that shows that essentially using deep learning frameworks, you can learn about the shape representation of people, and that then enables you to reduce down, in this case, to 2 views, but potentially you could go further than that. I think it's fair to say. And essentially what the deep learning is doing is learning what does the volume occupied by a person in general look like, and then taking some image constraints into that, which in this case are quite simple image constraints, just a couple of views, and the silhouettes from a couple of views, and using that actually to infer the full 3D surface. So there were 2 papers at ECCV from our lab. There were a couple of papers from other labs showing this kind of thing with quite nice results. Okay, I'm going to come back to what's on the bottom video in a minute. But essentially it's a deep learning architecture to encode body shape. I'll explain the thing on the bottom video. Okay, so just to give the snapshot, what this is doing in the end is we're learning effectively the mapping from a couple of views and the silhouettes that we might get of a person from those views, which gives us some sort of volume that the person might occupy. But you can say that this is not a very good model of the person. And we're learning the mapping between that using an encoder-decoder to get to a much richer surface detail. And the question is, really, can you set this up as a deep learning framework, and will the deep learning framework then be able to generalize across different people and handle this kind of input to learn what should the output be? So the input, just going back to the input, is just the silhouettes from a couple of views, and you'll see there's a lot of clutter that comes in there when the person's moving around. And we're learning effectively the mapping to then the reconstruction from a much larger set of views, so the kind of thing I've shown earlier on. Okay, so this is some of the test sequences. Just a comparison here of kind of the input to the system and what's coming out of the system, and hopefully what you can see from this is that the output is much cleaner in terms of the silhouette of a person, or it's actually a volume of a person, than the input, even when the input is degraded quite a long way. So whether it gets very blocky or there's bits of the surface missing. Okay, so I'll now explain this. So this is the kind of input volume we've got. This is what we're estimating from the red guy, is what we're estimating from 2 views, and the green guy is the reference, the ground truth reference effectively of our reconstruction from 8 views there. And the interesting thing to me here is that actually the red and green guys are very similar, even though what we've given the network is this one over here. And that means our network is able to learn actually, what the shape of a person should be, in very general terms with clothing and things like that, and allow us to infer that. There's a question here whether you can go even further to 1 view, and there was certainly some very nice work at ECCV also on looking at how you can do this sort of thing with a minimal set of views, I think with 4 views, and end up with the kind of detail of surface reconstruction that you get from state-of-the-art stereo on 16 or more views. Very comparable work to this. So it's a kind of interesting direction. It feeds very much into, I guess, the discussion for this workshop. So I'll allow Andy to give much more detail on that later. The other nice things are that once you've trained it, it's very fast to run. The reconstruction is potentially very fast. So, compared to where we've come from of having to use large numbers of cameras, and you think of things like the sports applications we have, this potentially is a solution to a lot of the things we've been battling with in those contexts. Okay, so I have another 5 minutes or so. I don't know how I'm doing for time. Okay, so I'm going to finish off by talking about one of the application areas, really, for some of this work, and something that we're picking up and taking further at the moment. Again, work from Armin and others, and this is a project we did, actually finished up last year, with Figment Productions, who are a VR production company who do kind of location-based VR experiences, Thought Park and things like that. And the Foundry, who many of you will have heard of, who make tools for visual effects. So the Foundry's interest is in how to use multi-camera systems and create content, and provide tools to create content for things like VR. And Figment's interest is actually in driving the production of content. And what we're trying to explore in this particular project was how can you use video content to get very realistic characters? So one of the experiences that Figment had created was Darren Brown's Ghost Train, which is, I think, at Alton Towers. Just getting muddled up. And one of the challenges they had in that was how do you create characters and composite them into a very realistic scene and still have them looking natural. And their expertise is in traditional animation. From that perspective, that has its limitations, particularly when you've got an interactive experience, very difficult to do and have the characters look realistic. So they were interested in what other methods of content creation. And this is kind of an open problem for the industries that are looking at augmented and virtual reality. How do you get realistic or believable content into those where you're trying to composite it with things that look realistic? So it's quite different from a game setting where everything's CG or a film setting where it's all done offline. It's to be interactive. So that's where we've been looking at some of these things. And in this case, we're picking up on work of light field technology, which is camera arrays. So a lot of work went on from the Stanford lab and places like that on light field arrays, probably 20 years back now. A lot of this work originates from, I think. And the thing about light fields is you can generate this. You capture a very dense set of views, and then you can render any view within that space and it looks photorealistic. There were some really nice results on static scenes where you've got highly specular objects, but because you're not doing any reconstruction, all you're doing is re-rendering views, it looks fantastic. So the question here was, well, can we utilize some of that, but in the context of people? So there, you can see here they're using 300 plus views. So this is something we used. This is our light field array. It's actually a sparse light field, but 25 cameras there, grouped. And the idea, you can change the spacing of your cameras, but the idea is within that space to be able to create any view of video sequences of the actors. And the reason for being interested in that is actually when you're in a VR headset, you tend to move around to look at the object. That's one setting, particularly if you're seated, which they happen to be in Darren Brown's Ghost Train. That's one setting. So it's not complete free movement, but it's kind of leaning into the scene, as it's called. So we're picking up this framework, which I've explained, and using that for that. The challenge here is that, of course, when you capture even 25 video views, you've got a lot of data. 25 video sequences, so how do you go through and put that into a form that you can render in real time on a headset, through Unity or something like that. So the way to do that is to take your sequence and introduce both 3D reconstruction and temporal coherence to it. So it builds on all the building blocks that I talked about earlier. So you've got this dense flow going on and ending up with a 3D reconstruction which is temporally coherent in terms of the geometry underlying it. You then have to put the image information on top of that. You perform similar things to compress the image information in terms of similarity of appearance between all of these views. But of course you want to also keep the change in appearance that you have with your light field. So you can effectively do a compression that allows you to do that. So we've got a camera array coming in, we reconstruct a mesh. We then effectively establish temporal correspondence through the light field scene flow, and we end up with a temporary coherent model from that. So I've explained all of that pipeline. Okay, so our cost function effectively has two terms. The one difference really here in terms of what we're doing is that because we have densely spaced cameras, we can use that as a constraint when we're doing matching and reconstruction. So rather than pairwise matching between cameras, we're actually matching across rows and enforcing epipolar image constraints in that context, which I think is illustrated here. So this is something that's been used before for dense light fields, and this is a kind of slice through a dense light field. What we have is effectively 5 epipolar lines that we're matching across. So it's a much sparser constraint, but it turns out that that still helps you in terms of the reconstruction that you're doing and in terms of the correspondence that potentially you're doing across views. We'll go into detail of that, that's all the other bits. So what we end up with is this temporal coherence as shown by the colour map here. And these were some actors that were put into the film production. So you've got a series of short sequences, and this is the kind of, this reconstruction is important because it's what allows us to then transfer this data onto a headset and have kind of real-time interaction. So get through this. Just one more sequence. So the real interest here is in things that are quite close up, so you get the effect of 3D. If things are distant, then you get less effect anyway in the headset. Okay, so I'll just run through this video. So this is the kind of setup we were using. It will also go into some of the other tools that were developed by the partners. So this is the camera array. So what we're doing here is capturing various different test sequences. It was driven by a production put together by Figment to test various things around what's the experience in VR when you do these things. And then the tool chain that was used was effectively to do the reconstruction temporal on our end, and then to use the Foundry's Nuke platform and some extensions to that to then allow artistic, creative editing of those things to composite into a scene. There's also a component of the project that was looking at scene capture using LiDAR and 360 video and that kind of thing, also to put it into scene content, but that's mainly to do with the background of the scene. So this is the elements of the actors, very standard nuke frame, and important things that are done in production, like separating out elements, removing clutter in the scene. All of those things need to be there, and probably even more so when you're dealing with surround scenes, where you can see in all directions. That's the scene framework, and you'll see the actors put into that frame. Okay, so this goes on to show it in a headset. You really need to be in a headset to see what it's like. And that went into a production, so it's one of the AR productions using this kind of light field technology. Interestingly, if anyone knows Lightro in the US, they were also developing this kind of camera array technology as the solution to put live content into video. And this, although Lightro have now gone bust effectively, I think officially bought out by Google maybe, but there's a lot of interest from Google and Facebook and others about, if VR is going to be a success, or augmented reality, how do we really put this kind of content in there that's derived from video and looks realistic? Okay, so that kind of brings me to a close. Hopefully I've given an overview of work we've done in 4D vision and some perspective on where, at the moment for us, deep learning comes into this. The challenge, there's a big challenge around data sets and what we'll do, but it has some potential to open these things up. I think the key there is, and particularly what we've found to be successful, is to combine different cues within the same optimization framework or within the same deep learning framework. And that's really key to ability to understand and model real world scenes. It goes beyond what people do, for instance, in terms of understanding scenes. But there are still lots of challenges there. It's certainly not solved. I was like to show the horse example at the bottom here, which was some footage from a little while back, which looks very cluttered. It's a multi-camera capture and reconstruction. What's actually being reconstructed there is the dust that's lifting off the ground, and it's the kind of thing that when you go out and shoot in the real world, you've never thought about. It's more complex, and I think if you think about that in a deep learning setting, in order to cope with that kind of problem, you have to have examples of dust. Yeah? You have to have something that deals with that. And it's, that's one of the issues we have when we turn to deep learning to solve all these problems is actually, deep learning is very poor at generalizing. It's very good at interpolating between examples, very powerful in that context, but very poor at going outside of that. And I think we have to be aware that it's not the solution to all our problems instantly. And we're trying to interface essentially machine sensing to the real world. There's a lot of complexity in the real world in terms of the things you really see. So that's one of the things certainly we've learned, but I think it's very applicable in this era of deep learning where we are advancing very rapidly on some of these things. Thank you.